Okay, so with the rational functions now, we're going to continue on, and today we're going to talk about all the discontinuities with rational functions. So why these functions or where these functions are not continuous. So we're going to look at the graphical and numerical approaches of this. And as we see, we kind of have this chart that's going to break this down on the different discontinuities, and we're going to have examples of each. So this will really break it up so you can see each type of discontinuity. So we'll go through that. And then on the back we have a little bit of analysis we'll go through with a few graphs. So let's go ahead and start down through this organizer that they have here. So for discontinuities with the rational functions, somebody get the door please. Okay. Should they vote now and then you're going to collect it?
Yeah.
Okay. So when they pass this out, take a minute, go ahead and vote, and then we'll get started with the notes.
Here you go. Yeah.
We have a senior up front.
Oh, I'm so sorry. Here we go.
Do you want them to fold the papers or leave them straight?
Just leave them. Just leave them. We'll be back. Or someone will be back.
Okay.
Thanks, guys. Exactly.
After you guys vote, I'll collect them so when they get back, if they can just take them. So when you're done, I'll take your paper. Anybody else still have one? Alright, so back to the discontinuities. If we look at this chart that's on the notes here, it really breaks it down into individual examples. So for the discontinuities, there's two types of discontinuities. We're going to be learning about a removable discontinuity and a non-removable. And if we break those down, we're going to have three different categories. So if we look specifically, we're going to look at the removable. So a removable discontinuity is the same as a point, or in other words, a hole. So a removable discontinuity is a hole. So if you have a hole in your graph, what do you think the description of that graph is? How can you describe your line? Like physically, what's happening with your graph when you have a hole in it? Yeah, the line's coming towards some point. That point isn't there, and then it continues on. So, two pieces of a graph. because it really, the whole splits it up, one side and another side. So two pieces of a graph connect at the same open circle. So that's what's happening at a hole. Did you have a pass from the office or no?
Yes.
Okay. I was going to say, because I had to mark you absent since you weren't in here.
Well, it's not for the office, but I can get one.
Yeah, you'll have to go to the office since I marked you absent.
That's fine. Right now?
Yeah, you should probably go now to let them know. If you want to take this pass with you so they know where you were. Sorry about that. Thank you. Alright, so the graph below has a removable discontinuity at x equals 1. So if we look at this graph, we have a line coming from the left. It is approaching 1 here, but there's an open circle, and then the line continues on. So that's a removable discontinuity. It's approaching this number, the y value of 1, and then it continues from 1 and continues on. So let's go ahead with this graph and figure out what the domain and range would be. What would the domain be? What would the domain be? Go ahead. Yeah. Negative infinity to 1, union 1 to infinity, because we have that hole at 1. Now we want to talk about the range. So what would the range be? What is the range of this function? Not quite. I like your reasoning, but not exactly.
Oh, wait. No, it actually is
Exactly. Negative infinity to positive infinity. Because every value of y has a value somewhere. So the range continues on. It goes down towards negative infinity, up towards positive, and if we see, even though we have a hole here at 1, there's a value over here at 1. So every value for the y has some type of answer for the domain. And then for this analysis, if we're talking about this discontinuity here, we're going to be doing analysis on the back that sort of looks like this. So I want to say as x approaches 1 from the left. Does this notation seem familiar to you guys? Okay, so as it approaches 1 from the left, f of x approaches what number? So if you're following your graph from the left side, what number does your function come close to? What value is it approaching? Rebecca? As we're coming from the left following the line, what number does it approach when you get towards 1 as an x value? What's your y value? Not quite. We're stopping at x equals 1. So you're going to x equals 1, so look at that x value, but you're coming from the left side. What number is it getting close to when you get to x equals 1? Emily? Yeah, your y value would also be approaching 1. If you plug it in, we don't exactly get 1 because we have a hole there, but that's where it's approaching. It's going near 1. As x approaches 1 from the right side, f of x approaches what? So if you're following your graph from the right side and going towards x equals 1, what number does it go close to? 1. And we're going to talk about this a little bit more with some other examples. But the removable discontinuity here, or the hole, that's whenever you can approach from both sides and they would meet at the same value. See how we have 1 and 1? We're going to get some other values where this may not happen. So if they end up being the same value, that's just a hole there because they're going towards the same point, but that point doesn't actually have an answer. Any questions about the removable discontinuity? Okay, let's go over to the non-removable. Everything good now, Marie? All right. The non-removable now. The non-removable is broken up into two, an infinite and a jump. By the infinite, they mean a vertical asymptote. Vertical asymptote. So a description of the graph. If you have a vertical asymptote, what is your graph actually doing? If you have a vertical asymptote, what can you physically tell your graph is doing? Right?
Coming close to that vertical asymptote that I'm actually touching it.
Okay, that's true. It's getting really close without touching it, but where is it headed? It gets close to touching it, but where is it headed? If you think about a vertical asymptote, it's either going this way towards where, or it's going this way towards where? Maddie? Exactly. We have two pieces. They approach infinity and / or, because depending on the function they could both go that way or opposite way. So infinity and or negative infinity, because of the vertical asymptote. So two pieces approach infinity and or negative infinity because of the vertical asymptote. So we'll look at an example of what that actually means. So the graph below has an infinite non-removable discontinuity. So what we just described above, this is an infinite non-removable discontinuity at x equals 1. So at x equals 1, they're talking about this line right here. That's the vertical asymptote they're talking about. So the description of the graph that we just discussed, this line on this side, it said it has two pieces. Here's the first piece, here's the second piece. The first piece is going towards positive infinity. The second piece is going towards negative infinity. So that's what it means by the two pieces going towards positive or negative infinity. All right, let's go ahead and figure out what our domain would be. What is the domain of this function? Remember, domain, you think x values? You can help me out. Go ahead, Marie.
Negative infinity to 1 of the union and 1 to infinity.
Very good. Negative infinity to 1 and then 1 to infinity. What about the range? How about the range? Go ahead.
Negative infinity to infinity.
Yeah, all values. Every value of y has some answer. Okay, so now we're going to try to do that same type of analysis that we did on the first problem. So we're going to write as x approaches 1 from the left, f of x approaches. So again, we want to go towards the x value of 1 from the left side. So put your finger or your pencil on the left side and go towards 1. And as you go towards 1, what is your function going towards? As you go towards 1 for the next value, what y value is your function going towards? Ashlyn? Positive infinity. It's going to keep going because Marie said it's never going to reach that asymptote. It's going to keep going closer and closer but never reach it. As x approaches 1 from the right side, f of x approaches what? So start on the right side of your graph. All the papers are there on the desk if you just want to hand it to them. Thank you, Tori. So we're starting on the right side, and if we go towards x equals 1, where is our function approaching? Negative infinity. Do we see how on this one we're not going towards some value that's the same? Even if we were going towards infinity and infinity, do we see how infinity we could be, it's still two different values because we actually don't know where we're approaching when we go to infinity. So that whole is whenever we approach the same value. This one, we are not approaching some similar value. So that is the non-removable infinite, also known as the vertical asymptote example. All right, let's look at our second non-removable. It's known as a jump. So a description of the graph. Well, we're going to have two pieces. That do not connect. But approach two different y values. So two pieces that do not connect but approach two different y values. So below it says the graph has a jump non-removable discontinuity, at x equals 1. So if we look at this graph, we see that it has two pieces, just like we stated up above. But we have a piece that stops here, and we have another piece that stops up there. It looks like it has to jump from one to another to get to it. So that's why it's called a jump non-removable discontinuity. So in terms of this specific problem, what would the domain of this problem be? Marie?
It would still be negative infinity to positive infinity because one of the poles is closed.
Yeah, if we look here, on this function we have all these values. That's going towards negative infinity. We come to 1, well this is open. So as of right now we don't have a value there. But then we jump up above to our other function and that hole's filled in, so we do have a value there. And then it goes towards positive infinity. So all x values, so the domain is negative infinity to positive. What about the range?
Again, it would be negative infinity to positive infinity
Very good.
because there's a line passing through that says
Yeah, this one's going up towards positive infinity. Again, it's going slow, but it's going up towards positive, and this one is going down towards negative infinity. Okay, let's go ahead. I'm going to erase this so I have some room here, but we're going to do that same analysis on the bottom for this graph. As x approaches 1 from the left, f of x approaches what? So go on your graph, start on the left and go towards x equals 1. What number do you approach? What number is your graph going towards? 1. Okay. As x approaches 1 from the right, f of x approaches what number? So start on your graph on the right side and go towards the x value of 1.
4.
It approaches 4. So this time we see we get two number values again, but those values are not the same. So again, if you think about that, if you find out where it comes from the left and the right, if they don't match up, can that be a hole in your graph? No, it has to be a jump because they're at two different spots. The hole can only be where they meet up, but they don't have an answer at that meet-up spot. So over here again, where the hole is, you're going to approach the same value. It's just an open circle at that value. For the jump, you're going to get values, but the values are going to be different. Any questions about the front at all? All right, let's go ahead to the back. So we see we have a graph, and they give us the equation there of our rational function. And we're going to look at this graph a little bit, analyze it a little bit, and answer the questions there. Alright, so if the coordinates of the hole in the graph are 3, 7/5, so that's right here. They show that hole in the graph. Complete each of the following statements with a value. So the first one, as x approaches negative infinity, the graph of f of x approaches what? So as x goes towards negative infinity, the function goes towards what? So negative infinity, we're thinking about going to the left. So let's start with the left piece. We're going towards negative infinity. What y value does that approach when we're going towards negative infinity? Ashlyn? 2. Okay. Next one, as x approaches positive infinity, the graph approaches what? So right here, we're approaching positive infinity with our graph. See how we're going towards positive infinity. What y value does this approach? What y value does that graph get close to? It's going towards positive infinity. Maddie? That is also 2. Okay, the next one. As x approaches 3 from the left, and you can also write that notation if you're given 3 with a little minus sign like I did on the front. That's the same as saying approaching 3 from the left, so if you want to put a minus sign right above it, kind of where you would put the exponent. So as x approaches 3 from the left, the graph of f of x approaches what? So we're approaching 3, but we're approaching 3 from the left side, so we're coming to 3 from the left side. What y value do we approach? Approaching 3 from the left side, what y value do we approach? Ashley? 7/5. Yeah, they told us up here the whole was 3, 7/5, so it's 7/5. Now it says, as we approach 3 from the right, a little plus sign there, the graph of f of x approaches what? So if you come from the right and you approach 3, now again, we said there's a hole in our graph there, so what should it approach? Think about your chart on the front. If you have a hole, if we're approaching the same spot from the right now, what should our y value be? What should the y value be? Go ahead, Ashley. 7/5 again. Yeah, we're approaching that same hole. All right. As x approaches -2 from the left, again a little minus sign, the graph of f of x approaches what? So approaching -2 from the left. We're approaching -2 from the left. What is the y value that we're going towards? Marie? Yes. So similar question as we approach -2 from the right side now. So we're going towards -2, but we're going from the right side towards -2. What y value do we approach? Going towards -2, but we have to come from the right side. So follow the graph, Marie. Negative infinity. Okay. Domain. Let's go ahead and figure out what the domain of this function is. Again, x values. Go ahead, Marie.
It would be -infinity to 2.
Close. Not 2.
Sorry, -2.
Yep.
And then there would be a union, and then it would be -2 to 3. And then another union will be 3 to infinity.
Yep. Very good. And this time, range. We have to be a little careful with the range. This one's different than the examples we had in the front. You think you have it, Marie?
Negative infinity to 7/5.
7/5. Okay.
A union 7/5 to 2. And then another union 2 to infinity.
Yes. So negative infinity to 7/5, 7/5 to 2, and 2 to infinity. That's your range. Okay, before we actually move on to the next example, I want to show one more thing. So we analyzed this graph a little differently than we have in the past. We drew some lines. We said that x was approaching some value from the left or right, and we were able to find domain and range. Before, we would have factored this, and we could have figured out some information. So f of x, let's go ahead and factor it and see if it makes sense, or we can figure out the same answers we had from before. So what is the top going to factor as? 2x squared minus 5x minus 3. I think this is one of the same problems we worked with yesterday, but we need to factor this. We're going to factor top and bottom. When you get any of the factors, let me know. Where you have something? Okay, what do you have, top or bottom?
The top one.
Okay.
So it would end up being x minus 3 and then 2x plus 1.
Okay, those are the factors on the top. Who has the bottom? Who has the bottom factored? Rebecca? Okay, x plus 2, x minus 3. Okay, so we're not going to really do any formal writing of answers of this, but we want to look at this and analyze it compared to what we found over here and our graph up above. So just looking at our factored form now from the information we learned yesterday and the day before, just looking at this, what do you think you can tell me? We're not going to write anything formally down, but let's just talk about it. Looking at this, from this, what can you tell? Marie? Okay, so in the denominator, Marie saw that if you plug in -2 or if you plug in 3, you're going to have some kind of undefined answer. So we see that we do have undefined answers there. There's no answers that exist. Okay, so that's one thing that you can tell. Just from looking at this, would you be able to tell what type of discontinuity? How do we know, if we're looking at just this, if our discontinuity is a whole? We did learn part of this yesterday and the day before. Think about our factors on the top and factors on the bottom. Really look at them. How can we determine if there's a whole? Yeah, this one that's on the top and the bottom. Remember we talked about those canceling and non-canceling terms? So this term that cancels with the top, remember if you plug in -3 in here, you get 0 on the bottom. If you plug in 3 up here, you get 0 on the top. If you have any type of answer 0 over 0, we said that was undefined, but that represented a hole in the graph. So we know that this x minus 3 factor would cause a hole in the graph. The x plus 2, does that cancel with the top? No, so we know that has to be a vertical asymptote. So the one that cancels is a hole, the one that doesn't cancel is a vertical asymptote, and if you look at the graph up above, that's exactly what happened. We had a vertical asymptote and we had a hole. Now if you write a simplified version of that, yeah, the x minus 3's cancel, so I'm going to write it up here just because that's where I have room, but the function would actually be 2x plus 1 over x plus 2. That is your simplified function. Alright, any questions about this example? So we did that entire example together. Do you feel comfortable trying this one and then checking your answers? Work with a partner. So if you don't want to work alone, work with your partner. Try the bottom one. Try to answer all these questions on the right side here by looking at your graph and answer them according to how we answered the ones up above. So give it a shot. I'll give you a few minutes to try. Work with a partner if you'd like to, and then I have a few more notes to write down after you finish this. So we're not done after this example yet. Try to go all the way down, figure out the domain and range at the bottom too. Okay, the first one is x approaches negative infinity. What does your graph approach? G of x. What does it approach? The first one. Marie? We see it does approach 1. Yeah. So go ahead, check your answers. As we go to positive infinity, it also approaches 1. So as we go to negative infinity, we see we're going this direction. That's why it approaches 1. And as we go towards positive infinity, we're over here, so we're also approaching 1. Okay? As we approach 3 from the left, so from the left side we want to go towards 3, it approaches that 1/2. And again, they gave that to you up here, the negative 3 1/2. So from the left it approaches it. From the right, you also approach 1/2. So if you come from the right side, you approach 1/2. As you approach 1 from the left, so start on the left, go towards the x value of 1. You never really reach it because there's that asymptote, but we're going towards the x value of 1. Your y value is negative infinity. As you go to 1 from the right, you go towards 1, but you never really reach it with the asymptote. You're going towards positive infinity. And there are your domain and range values. So go ahead and check your domain and range. Any questions about that example? Any confusion? Any specific part you want me to go over on the board again? So again, anytime there's a hole, we see, so at negative 3 we have a hole, so it's approaching the same value. We have an asymptote, so it's going towards those infinities. So that all makes sense. And if you look, our factored form is actually here at the bottom. So if you did not write your factored form, go ahead and write your factored form. And we see that we do have a cancellation like up above. And it's at negative 3 where the hole is, and that makes sense because those are the terms that canceled. So if you want to go ahead and write that factored form. Alright, so we have a few things left to say. So after this example, we have a few notes to write at the bottom. So first note, canceling the denominator factor leads to a hole graphically. So we canceled those factors with the denominator. That leads to a hole graphically. The second note is the non-canceling denominator factor leads to a vertical asymptote. So we found that out. In this case here, the x minus 1, well at 1 we have the vertical asymptote. Up above, the x plus 2, at negative 2 we have the vertical asymptote. So the non-canceling denominator factor leads to a vertical asymptote graphically. And then substituting the whole x value into the simplified rational function will yield the y value of the whole. So substituting whatever the x value is of the whole into the simplified rational function will give you the y value of the whole. So what exactly does that mean? Well, let's look. We have the simplified version right here. So we know the x value of the whole in this problem was -3. So if we plug in -3 plus 1 is -2. -3 minus 1 is -4. And what did we get then? -1/2. And what is the y value at that whole? Or sorry, 1/2. What is the y value? 1/2. So if you plug in on the simplified version, again we simplified in both examples, plug in the x value for the whole, it'll give you the y value where the whole is, but remember, it's a whole, it's an open circle. Okay? Then the ratio of the leading coefficients that yields the horizontal asymptote graphically. So if you look specifically at this example here, the leading coefficient of this example is 1/1. The horizontal asymptote is at y = 1. If you look at your example up above, it doesn't fit on here right now, I have people copying, but if you look at your example at the top, the leading coefficients on f of x are 2/1. So 2. So there's a horizontal asymptote at y = 2. So those are some tricks that you can use whenever you're trying to graph these given a function. So those are some tricks to find out where the asymptotes go, where the holes go. And lastly, the non-canceling numerator factor leads to a 0 graphically. So that just means any of the factors on the top that don't cancel, when you set those equal to 0, that's where the hole is. Or where the 0 is, sorry, 0, not hole. The non-canceling numerator factor leads to a 0 graphically. Again, another term for 0, you could write x-intercept. 0, also an x-intercept. Now, from the standpoint of looking at the graph and your functions now, do each one of these definitions at the bottom make sense to you? We understand where they come from? This is the only one we really haven't tried here, the substituting the value. So remember, that's the simplified version. If you put in -3, you'll get the y value of your whole. All right, do we have any other questions? We have a little bit of time left. If you want to look at a few homework problems before the weekend, see what they're like, see if you're going to have any questions, but we will finish this section on Monday.